Let's move to lecture 4, diffusion mechanism. In these lectures, we are put more efforts or emphasize on a micro scale diffusion mechanism instead of macro scale, what we learned from lecture 3. In macro scale, actually, you use the diffusion equation, and we try to, as long as you know the flux, can formulate the flux, then you can easily get the concentration profile of diffusing atoms as a function of location and time. This is the diffusion phenomena you can observe in macro scale. And also we learned from previous lectures. So in this case, in your experiments, usually what will you do, or what do you deal with diffusion process in your experiments? People usually will measure the concentration profile during the diffusion process, right? Then you have chance to know the diffusivity, or you can estimate the diffusivity of your materials. And as you know, each material has its own diffusivity. So what diffusivity, what's the physical meaning of diffusivity, or what's the relationship between the diffusivity and your materials? Diffusivity actually describe how diffusing atoms moves along or in your materials. So diffusivity is highly related to material properties. So in these lectures, we are going to by investigate or introducing different kinds of diffusing mechanisms in crystals, then we will show you how to get or how to obtain the diffusivity of your materials. And what's the relationship between the diffusivity and atomic movements in crystals or in your materials? So in these lectures can be simply divided into two sections. The first section is we call the thermally activated diffusion. The atoms can move or diffuse through your materials due to these atoms have thermal energy. So as long as the temperature is higher than 0K, then the atoms definitely has certain thermal energy to allow these atoms to diffuse or move around in your materials. And in these sections, we are going to describe the atomic jumping process. What's the atomic jumping process? Actually, what's the diffusion? Usually you can observe the diffusion phenomenon, but in macro scale, right? But if you enlarge your materials, and actually diffusion phenomenon means lots of atoms jump together. So this is what we call atomic jumping process. So you need to have some idea how atoms move or jumps in your materials. And in this lecture, there are two different jumping process. The first one we call is a random walk. That means this jump is nothing related to previous jump or next jump. We call it is a random walk, a random jumping process. And the other one is we call it is a correlated atomic jumping process. That means this jump is correlated with previous jump or next jump. So for example, like if we have a pure metal, and the atoms can diffuse through what? Exchange with vacancy, right? So this is how we call it. This kind of jumping process is a correlated atomic jumping process, because the atoms the only way to allow these atoms moves or diffuse is through exchanging position or location with surrounding vacancies. So you need to have vacancy, then these atoms can jump, right? So this is, we call it is a case of correlated jumping process. And the second sections, we are going to give you some more real examples. We are going to talk about the diffusion in different crystal lattice. So first one, we are going to talk about the atomic diffusion mechanism. Actually, through different, depending on different crystal structures, then atoms have different diffusing mechanisms we are going to introduce to you in these lectures. In these parts, actually included what? Included vacancy-mediated diffusion mechanism. This is what we talk about. The atoms changes location with surrounding vacancies. So this atom can make a successful jump. And the other will be, the second one we are going to introduce you will be, for example, like interstitial diffusing mechanism. That means the atoms diffuse through interstitial sites, something like that. So we are going to introduce different diffusing mechanisms in different crystal lattice. And the second part, we are going to talk about how about if the materials is ionic solids. Does it affect the atomic diffusion? So how the ionic solid materials affect the atomic diffusion process? So we are going to introduce in the second sections. So let's move to the first one, is entitled Thermally Activated Diffusion. And don't forget, in these lectures, we are going to try to correlate the diffusivity with atomic jumping process. Diffusivity is what you can measure in macro scale, and you can observe this phenomenon in macro scale, right? So how to correlate the diffusivity with atomic jumping process in micro scale? So first of all, we need to know what's the thermally activated jump. Actually, it is a series thermally activated discrete movements or jumps between neighboring positions of local minima energy. So it would be neighboring positions. For example, like 1 and 3. Position 1 and position 3 actually is a neighboring positions and also with minima energy state. So how these atoms, blue atom, purple atoms moves or jumps from location 1 to location 3. So we try to draw the energy, the potential energy as a function of location, and you find that at location 1 with a local minima energy, and also location 3 with also the local minima energy. But if this atom need to make a successful jump from 1 to 3, you can find that at location 2, its energy has a higher energy barrier, which we call it as a delta E activation energy. Some people call it as activation energy or energy barrier. And this energy barrier actually is due to if this atom is going to go to location 2, this will cause the lattice distortion, right? So this atom need to have higher energy to overcome this energy barrier, then it can successfully move to location 3. So if this purple atoms move to location 2, that will cause a local lattice distortion. So we call it this is a excited state with higher energy. And so then it can make a successful jump to location 3. Because from location 2 to location 3 is spontaneous process, right? Because the energy, this jump can decrease the total free energy of the system. So this will be the spontaneous process. So as long as the atoms at location 1 have energy higher than energy barrier, then and also there's a vacancy at location 3, then the atoms at location 1 can make a successful jump to location 3 as long as it has a thermal energy or energy higher than this energy barrier. Otherwise, if these atoms with energy lower than this energy barrier, then these atoms just vibrate or move at this location 1. It's not going to make a successful jump, okay? And the energy here, as we mentioned before, is only thermal energy. As long as the temperature, environment temperature is higher than 0 K, then we can estimate, then we can simply calculate how many atoms has energy higher than this energy barrier, right? Okay, so if you try to use the classical mechanics to exactly calculate the vibration or jump rate of these diffusing atoms, how to do that? So in classical mechanics, first of all, we can plot the energy function as a least square function. And at the bottom, the energy we call is E well. And at the top, this is like a location 2. We call it as EA, is the energy at activated or excited state. And what's the L well and tau well? The L well is the length of this well. And the tau well is how much time of these atoms stay at this well. We call it the tau well. So you use the length of this well divided by time spent on this well. So this is the velocity, moving velocity of these atoms. And we use the same concept and get the LA is the length of this well, and the tau is how much time of this atoms stay at this well. So we call it tau A, and we use the LA divided by tau A is the velocity of this atom at the excited state. Okay, and EM is the energy barrier, or we call it activated energy, is equals to EA minus E well. So this is the difference between this well and this well, between the unactivated state and activated state. Okay. So the thermally activated jump actually is atoms jump from low energy state toward to activated state. And next step, definitely this atom is going to, as long as these atoms jump to the activated state, to decrease the total energy of a system, this jump definitely is a spontaneous process. So if you want to, if we are interested in the jump rate, so the rate limit step will be how many atoms have energy higher than this EM or EA. Oh, okay. So EM to allow these atoms to jump to the activated state. So as we know, This is the numbers of particles as a function of energy. So this is Boltzmann distributions. And if the temperature is at T1, and we know we only have this small portion of atoms have with higher energy, higher than EM. So this portion of atoms, these numbers of atoms can make us successfully jump from this low energy state toward to this activated state. While we increasing the temperature of environment to T2, then you can observe this curve shift to the right-handed side. And here you can observe that more numbers of atoms have sufficient energy to overcome this energy barrier. And the exactly portion of numbers of atoms we can estimate by this equation is proportion to exponential minus energy EM divided by KT. And based on this assumption, actually we make an assumption here is we ignore the quantum tunneling effect. That means the atom, the only way to allow these atoms to move to this position 3 is through position 1 to position 2, then jump to position 3. We ignore the tunneling effect. That means the atom is not going to go to position 3 through tunneling. Okay, so we have this background idea. Then next is how to get or obtain the atomic jump rate. This is jump rate means the successfully jump rate is the atomic vibration frequency times the probability of atoms to cross the barrier. So the probability of crossing the barrier, this is the term is this Boltzmann distribution term, because this is a probability of atoms have a higher than EM, higher than energy. Then you can have some idea about the probability based on this term. So in order to get the atomic jump rate, you already know this term, right? Is this. So what's the atomic vibration frequency? Based on classical mechanics, if we assume the atomic jump rate is along one specific direction, is along this direction, based on this assumption, so it's along to right-handed side in specific direction, then the gamma prime, the atomic jump rate in specific direction, is equals to atomic vibration frequency times the probability term here. And the first term is atomic vibration frequency. Actually, this term you can consider how to estimate that. Based on classical mechanics, we can get the v velocity of this atom can be expressed like square root of kT over 2 pi m. This term you can consider as kT is the thermal energy. So the energy divided by the mass and take the square root of it, you can consider roughly it's like kinetic energy 1 over 2 mv squared equals to kT, something like that. So when you want to know the estimate the velocity, you can find it's a kT over square root of kT over m. But you still have 2 pi here is regarding to some other considerations in classical mechanics. If you are interested in that, you can check the books in classical mechanics. But velocity divided by the length of this well is what is the frequency, right? The velocity is the length divided by the second, right? And you over the length, so the rest of part is 1 over s seconds. So it's a unit for frequency. So this is atomic frequency times the probability. But this is in classical mechanics. In classical mechanics, we assume the atoms do not interact each other. So it's independent atoms. But it is not real, as we know. when we talk about the crystal structure, we believe, based on the quantum mechanics, the atoms do interact with the other atoms in crystal structure, right? Sometimes it's different kinds of bond, including ionic bond, covalent bond, or mental bond. So atoms, there must be some bonds or some force exist between two atoms in crystal structures. Based on this idea, we need to modify the potential function as parabolic potential function in red here, which is described in quantum mechanics. After modifying the energy function as parabolic curves, then you can get the modified atomic jump rate as also the atomic vibration frequency, which is predicted by quantum mechanics by these parabolic curves, and also times the probability of the crossing the barrier, which is the same as what we describe in classical mechanics part. And regarding to the atomic vibration frequency, as you know, actually atoms in crystal structures has interaction between neighboring atoms. So based on these interactions, we call this kind, and in order to predict the atomic vibration frequency, then there's a model, very famous model, we call it as harmonic oscillation models, and the energy can express as 1/2 beta and x squared. X is the displacement, and the beta here is the force constant of the spring, and you can consider that as a bond strength. So I use the slide to quickly review what is the harmonic oscillation model. So in crystal atoms, actually, you can consider the atoms attached by a spring to each other. So there's a mass interaction between two atoms. And if you try to plot the energy as a function of location or displacement, then you can get this curve. And this oscillation can express energy can be expressed like proportion to the spring constant K and also the spring displacement Y squared. And based on series deviation, you can get this vibration frequency equals to this is proportion to square root of spring constant or force constant, and divided by the reduced mass is correlated with the mass of these atoms, so can be expressed like this. So we directly take these results and back to previous slide. So we got this is a modified atomic vibration frequency. So this result tells us that based on the quantum mechanics, the atomic jump rate in specific direction, gamma prime, is highly associated with bond strength, reduced mass of both atoms, and energy barrier, and also the working or environment temperature. So, and based on these results, you also can have some concept. For example, like beta is bond strength, and reduced mass is correlated with what kind of atomic atoms we are talking about. So beta is bond strength, so correlated with either like this crystal or this material is belong the okay. So the atoms interaction or bond is belongs to ionic bonds, metallic bonds, or covalent bonds. And how many bonds we are talking about? So it would be varied with atomic vibration frequency will vary with the beta, and also what kind of atoms we are talking about. And these structures, these crystal structures, what's the energy barrier and working temperature? So you can have some idea that the atomic jump rate actually is highly correlated with crystal structures and also atomic atoms, the kinds of atoms, what kind of atoms we are talking about, and also the working temperature. And this energy barrier usually is associated with the crystal structure, right? So now you have some pictures like atomic jump rate. Actually, if you want to have a higher atomic jump rate, then definitely you will have a higher beta, small m, and also a higher activation energy, right? Lower activation energy and higher working temperature. So if you want to have a higher jump rate, right? Okay, so let's move to, yes, you already know the gamma prime is an atomic jump rate along a specific directions. So how to correlate the diffusion phenomena with this you observe in macro scale and with atomic jump, which you observe in micro scale. So this following slide, we are going to try to help you to correlate the diffusion and atomic jump. So actually, what's the diffusion? Diffusion is a result of series of discrete jumps. So for example, if there's an atom, blue atom here, and after then next, this atom probably will jump to this direction, and next will be probably jump to this direction, and this direction is R3. This small r represents the displacement of each jump for these atoms. So after time tau, then and this atom is going to reach this location, and this capital R is a summation of each jump of these atoms. So we use a capital R to represent it. So also is a displacement. So what's the total jumps? Total numbers of jumps. We call it as n tau. N tau equals the gamma. Gamma is the atomic jump rate times the time period tau. So atomic jump rate actually is what? Is how many times of jumps per second. So you times how much time it's spent. So you got the total numbers of jumps. So we call it n tau. And this gamma is different with the gamma prime we just talked about. Please label it or mark it. This gamma is a total jump rate. You need to consider all possible directions, not only one directions. In previous model, which we simulate either is from based on the classical mechanics or quantum mechanics, we just consider the jump is along just one direction. Okay, so displacement of each jump, we use a small r to represent it. And the displacement after n tau times jump, we use a capital R to represent it. So you just simply summation the small r from 1, I equals to 1 to n tau, then you can get the displacement after n tau times jump with a capital R to represent it.